Hi, my name is Sergio Moreno, and I'm going to make my presentation about the electro-hydraulic rolling subwheel. Well, as you can see in the index, we're going to discuss about the introduction, then we're going to make a research about the electromechanical design, and then the hybrid dynamics model and the model predictive controller design, which are the most important parts of this rolling subwheel. Then I'm going to make my conclusion about this article. Well, the introduction. Rolling, we have to say that rolling exhibits a high degree of mobility, inherent stability, and self-recovery from collision when you compare it to other robotic locomotions such as leg, crawling, and hopping. And it is much more effective. More advantages that these systems have is like they can carry payloads, they provide protection to internal electrical and mechanical components, and they can navigate difficult environments. They have two operating principles. The COM is like the shift of the center of mass of a cylinder or a sphere away from its neutral position, and they have internal components such as servos, gears, and motors. And then we have the systems with the ability to deform their geometry, which are characterized by their modular links that can interact with the other models and create global deformed shapes. And they can work in single mode or multi-mode. The shelves of both systems, COM or deformed geometry, can be soft or rigid. Well, the most are soft, and in this article we are going to make the research about the Hassel-driven self-rolling wheel, which, thanks to its hybrid structure of soft actuators placed around a circular rigid skeletal frame, it demonstrates much faster rolling characteristics despite being a little bit heavy, like 979 grams. We're going to start with the mechanical design. This will consist of 16 folded Hassel actuators, a modular cylindrical frame, an onboard printed circuit board, a PCB, and an experimental platform. Okay. Now you can see the mechanical characteristics from the actuators, the electrodes, and the dielectric used. And then we have to say that the cylindrical frame consists of two circular rims with this diameter, and they have 16 actuator pads, as I said before. This design allows the wheel to roll on the rigid frame and minimize the contact friction between the actuators and the ground. The PCB commands and drives all the actuators, and it is sandwiched between the two circular rims that the wheel have. And then the wheel is mounted to an axle that can pivot around the center of a platform. Okay, we are getting in the electrical design. The most important things about the electrical design is to talk about the components that are the PCB, that has three groups: the power delivery, the driving and control group, and the sensing group. Then we have to say that the power delivery is composed by one DC-DC converter, and a step-down linear dropout regulation, a down linear dropout regulator. Okay. The regulators provide the power to the driving and control group and to the sensing group. Then the driving and control group consists of a microcontroller that communicates with a personal computer in use, and the microcontroller processes sensing data coming from the sensing group and is transferred to the computer. And this computer, depending on the data, generates an open loop or closed loop commands. And then these commands are transferred to the HV switching circuit that has 16 units to drive 16 different actuators. And the sensing group is a single supply operational amplifier for HV and current monitoring, and has an absolute rotary encoded. And we have to say that the PCB has asymmetric component placements. Well, as you can see, this is the important schematic of the hybrid dynamics model, and then we're going to talk about the dynamics modeling of the software. Well, this could be the most important schematic of the dynamics modeling of the rolling software. Then we can see the 3 reference frames required for the dynamic modeling of the rolling motion. These are in this part we are describing all the as you can see from up to down, we are describing all the elements that that have to be taken into account to make the formulas and extract all the physics and all the elements and components of the dynamics, such as the velocity of contact and the velocity of the wheel's COM. Okay, then talking a little bit more about the dynamics, we denote the point G as the COM of the pivot arm, and we have the kinematic constraints of the rolling software, and we have to talk about the kinetics of the pivot arm with the U-mount. We have the reaction force at the pivot elbow, we have the weight of the pivot arm, we have the resultant reaction force from the wheel on the arm, we have the pure bearing friction torque, and we can consider also the angular momentums of the pivot arm. And then we have the kinetics of the Hazel rolling wheel. We can say that the wheel is going to be treated as a cylinder. We have the weight of the wheel, we have the reaction force to the ground again, we have the simplified reaction force from the pivot arm on the wheel, and the torque and the friction. Then we are introducing the hybrid state space model of the rolling software. We have to say that E1 represents the angular position of the rolling software with respect to the 16 actuators and the ground. Then the angle E1 may be two different values, and depending on the value, we are talking about the actuator 0 or the actuator Y. Could be from 1 to 15. Based on the E1 angle, we can determine N and the actuator which is in contact to the ground. To talk about the force that is applied by each actuator to the wheel, it depends on 3 inputs: the activation angle, the deactivation angle of the actuator, and the target actuator. Then the operator of the electro-hydraulic rolling software. We have to say that initially the Hazel rolling software has an activated status 0, activation angle down counter 0, and deactivation 0, and carry actuation index is also 0. When you have E1, you can determine the current actuator, then enter the jump map, and you can when you enter the jump map, you can update the condition, and when you update the condition, the activation status switches from 0 to 1 at the autocapper, activates the actuator, and then when the speed 2 increases and the E1 decreases, you update again the condition, enter the jump map again, and the activation status changes from 1 to 0, and then it deactivates the actuator. Then we have the braking rules. To regulate the speed, the wheel can lower its speed by passively decelerating thanks to friction, or braking, that is more effective. The rolling soft wheel makes braking by activating the actuator in a direction such as the force component FA2 is opposite to the rolling direction. Then we have the controller description. Okay, the electro-hydraulic rolling soft wheel has jumps from state to state that depends on the discrete input U. And it's important to talk about the PSO algorithm to implement optimal inputs and to regulate linear speed. There's always a simulated speed and a real speed. The simulated speed is which the wheel attempts to track, and the controller generates an input U to minimize the errors between the two speeds, and the disturbance estimator accounts for real-time error that makes the deviation between two speeds. And we have two modes. The acceleration, it uses MPC and PSO to minimize difference between the speeds, and active deceleration, it applies braking inputs. Okay, and the cost function is the mean square error, and the PSO is in charge of making the cost function more near to 0. And well, we have the real-time implementation. Here we have to say that the program, when you enter the jam map, making all the updates on the activation status and stuff like that, the program shares data map all around, and the data collector writes motion capture and microcontroller data to the map. Then the data logger copies the data map into a text file, and the MPC pulls the content of the data map when wheel is activated, and computes an optimal control command input U and send it to the embedded microcontroller via the data collector thread. Okay, and then the embedded microcontroller sends the angular position, sends the activation status in every moment, and the current actuator index N, and the input U that we have in all times. And then about the conclusion, well, reading the article, I have seen that the wheel's performance is tied to the interplay between electrical, mechanical, material, and software design choices. Depending on what you choose, you will have a different design to the other. The thing that I like the most about this design is the actuation of the MPC and PCO to regulate the wheel's rolling speeds and making the error more zero possible. And I see that it is a sophisticated design that may be the first big step to create new and highly mobile soft robots in the years to come. Well, that's all my presentation. Thank you all for listening to me, and have a nice week.